After the discovery of X-rays by German scientist Wilhelm Röntgen in 1895, French scientist Henri Becquerel wanted to study the properties of fluorescent minerals to see whether they could produce X-rays after being exposed to sunlight. His experiment consisted of wrapping the minerals in dark paper and putting it on top of a photographic plate. After being exposed to sunlight, he would develop photos from the plate to see whether an image was created by the mineral or not. One day, when working with pitchblende, the day wasn't sunny enough for the experiment to work. However, Becquerel decided to develop the photos anyway. He found that uranium was capable of producing its own energy without the help of the sun. When testing the energy, he found it wasn't X-rays because X-rays were neutral and could not bend when exposed to a magnetic field. Using a special apparatus, he used the magnetic field and proved that the energy emitted by the uranium bended. This means that in 1896, Henri Becquerel had discovered radioactivity. Marie and Pierre Curie heard about Becquerel's discovery and were greatly interested by it. They decided to study it further, and Marie even named the phenomenon radioactivity. By 1898, they had managed to isolate two new radioactive elements, radium and polonium. The Curies were also able to identify radioactive properties in thorium. Rutherford carried out several experiments that helped us further our understanding of the atom and radioactivity. From one of his experiments, he was able to conclude that radioactive substances became less radioactive over time, and that decay could be described with a simple equation, half-life. In another experiment, he found that there were at least two types of radioactivity, alpha or beta. He then began classifying them by their ability to penetrate matter. In 1911, Frederick Soddy discovered that naturally occurring radioactive elements had a number of different isotopes. After the discovery of isotopes, J.J. Thomson showed using a mass spectrometer that isotopes were atoms of the same element that had different atomic masses. Then, in 1932, James Chadwick discovered the neutron, which helped us further understand the atom. Also in 1932, John Cockcroft and Ernest Walton were the first to produce a nuclear transmutation, otherwise known as splitting the atom. In 1934, Irene Curie and Frederick Joliot Curie are the first ones to create artificial radioactivity. In 1938, Otto Hahn and Fritz Strassmann discovered fission. Lisa Meitner and her nephew Otto Fritzsche calculate that the energy released from the fission was about 200 million electron volts. Fritzsche confirmed the figure experimentally in January 1939. The mass of an atom is found by adding the weight of its protons and neutrons. But if you add the mass of every single proton and neutron using the actual mass of a neutron and a proton in an atom and then compare that number to its actual weight, you will notice that some mass is missing. That missing mass was turned into energy, and it is what keeps the atom together. It is called the strong force. Now, the strong force is incredibly strong over short distances, which it would have to be if it was to hold the atom together. However, the strong force loses its strength as distances increases. That means that as nucleus grows in size, the less hold the strong force has over the nucleus, and because of the lack of hold this force has on the protons are more attracted to the electrons orbiting around the atom. This is not good because if the protons are able to go to the electrons, that's basically the atom collapsing on itself. This makes an unstable atom. Alpha decay is when the nucleus emits an alpha particle. An alpha particle is made out of two protons and two neutrons, which is basically a helium atom. When writing it out in an equation, the alpha particle is written the same way as a helium one. very not to scale. This, however, is. The amount of energy that the chemical reaction makes can't even be seen on the graph. Why does that happen? Well, in a chemical reaction, the energy release comes from the breaking of the bonds, ionic, covalent, whatever, between atoms. It's a lot, but the amount of energy that comes from breaking apart a nucleus, it's more. Way more. Because the amount of energy it takes to keep the subatomic particle together with the other subatomic particles, it's the same amount that it's released when it's removed. We can find exactly how much energy per atom by using Einstein's famous equation E equals mc squared, where E is energy, m is the mass in kilograms, and c is the speed of light. So let's try it out with a nitrogen particle. After we find the difference in mass, we plug that into the formula, in kilograms. Then we multiply it by the speed of light squared, and we get the amount of energy being released per nitrogen atom, around 1.64 times 10 to the negative 11 joules. That is a small number, sure, but that is the amount of energy being released per single atom. If we multiply that by Avogadro's number to find the amount of energy that will be released per mole of nitrogen, it will be 9.9 times 10 to the power of 12 joules of energy per 14 grams of nitrogen. To put that into perspective, the amount of joules of energy produced by a ton of TNT is around 4.1 times 10 to the 9. So nuclear reactions produce a lot of energy. Let's start with fission. Fission occurs when a heavy nucleus splits. The heavy nucleus can split any number of ways as long as the number of protons and neutrons in the products adds up to the number of protons and neutrons in the original nucleus. Fusion is when two small nuclei combine to create a heavier nucleus. This process creates more energy than a fission reaction because of the repelling forces the positively charged nuclei have to overcome in order to fuse together. These sorts of reactions don't occur naturally on Earth because of the conditions that need to exist for the nuclei to overcome the repelling forces. The Sun, however, is a perfect example of a fission reactions. Due to the extreme temperatures and pressures inside of the star, hydrogen atoms and helium atoms are able to collide and fuse together to create energy and more helium. Nuclear energy is formed via fission reaction. Nuclear energy has a lot of pros as an alternative energy source. It doesn't require as much space as solar power, and the amount of energy it creates is huge. However, it's not perfect. Most nuclear reactors use uranium to create energy, but uranium has lots of problems. First, the amount of uranium that's actually able to readily fission is very small. In order to use it, the uranium has to be enriched, and once it has, that uranium can be used to create nuclear weapons. This increases the price of the energy, as a lot of money has to be spent on security in order to keep the uranium from their own hands. Another problem is the nuclear meltdown. When the energy created gets out of control and the plant can't deal with it, disaster strikes. Think of disasters like Chernobyl or Fukushima. There is an alternative to uranium, thorium, which can reduce some of its problems. It can produce less nuclear waste. The plutonium it can create is way too dangerous to be used in nuclear bombs, and it, unlike uranium, can fission in a liquid core reactor. Liquid core reactors can turn themselves off if something goes wrong, basically preventing meltdowns. Despite that, there are still other problems with nuclear energy. Nuclear reactors are kept in water to help keep the reaction under control, and that water gets warm and it does get released back into a body of water. This causes thermal pollution, which can greatly affect marine life. Nuclear reactors are also very expensive to build. We still don't fully understand the effects of low-level radiation and don't know the health risks it may have. It bears repeating, But nuclear waste, and the more we store it, is also an issue. You might be wondering, why fission, if fusion creates way more energy? And yeah, it's true, it creates more energy. It also doesn't create nuclear waste, it doesn't create isotopes that can be used to make bombs. It's perfect, except that we haven't figured out how to control all that energy. Like I said, it's a massive amount. For blowing up stuff, it's great, but other than that, there's not a lot that we can do with it. Yet. And as I mentioned, the conditions needed in order for a nucleus to undergo fission are ridiculously hard to achieve. So, fission it is.